cord to this computer and find automating controls. Okay. I don't think I need the microphone. You all can hear me, right? Cool. So today I'm talking again about lipids. We saw lipids, some of you in the morning, right? We're gonna keep talking about, I think we already talked about proximate. Did you start with what, proteins already or no? Okay. But anyway, proximate, we're gonna do fat characterization. Before we start that, I would just, you all know me, but like a little bit about what we do in my lab, just so you have an overview and have a couple minutes. So my lab uses, so I'm an assistant professor of analytical and food chemistry. My name is Fernanda Diaz. My lab uses chromatographic and mass spectrometry-based methods associated with chemometric tools to actually understand the effects of processing, storage, and lipid and flavor. Right, so we work in the how like lipids will affect our flavor and flavor formation in food. This is just a brief overview of what my lab has right now. So we have a Vici working on flavor of milk protein concentrates to application in high protein beverage, all those Fairlife that has a lot of protein in it, right? How can we improve the flavor on that? Shahan that works on drying technologies of milk powders, Chelsea quality of plant proteins, how residual fat affects of flavor formation. Wellington, my postdoc, he works in several projects, but also in green extraction technologies to co-extract oil and protein. The same as he is a PAM actually student that, but she works with Wellington on co-extraction of oil and protein from hemp. I have a visiting scholar working on lipidomics, olive oil from Brazil and California. And I have Alicia working on quality of human milk, especially how process affect fatty acid composition and also of flavor formation, which is kind of fun in human milk. Some babies are very picky to flavor in milk. You can like have lipase liberate free fatty acids and then don't eat the milk. But anyway, this is topic for another class. In my lab, we also are training the next generation of research. We start very early. This is a baby girl. She's already doing some training on the GC. A little distracted, but this is my baby girl. She's 6 months, and this is Anna. She's already learning a little bit in the lab. Yeah. Anyway, back to crude fat analysis. People that were in my class this morning. Yeah, the following is true. One, the term lipid can be used for both oils and fat. B, oil has higher melting point than fat. C, fat has less saturated fatty acids as compared to oils. A, B, C, all the above. No. First question, oil is liquid or solid at room temperature? Liquid, right? So is C correct? Remember, more saturated means like lard is more saturated, right, than oil. So, okay, we know that C is out. What about B? Not correct, right? Okay, so what is left? A is correct. Or you guys can all see that? So the term lipid can be used for both. When we talk about oil has higher, is the other way around, right? Fat has higher melting point than oils, and the other way around as well with the other one. Oils have less saturated. Fat has more saturated, right? When you think about lard, butter, more saturated. Oils, vegetable oils, more polyunsaturated, linoleic acid, alpha-linoleic acid, and so on. Next question. So you take participation from, you are, okay, good. The lipid, the lipid portion of the food for people that also were in the class this morning can include vitamin A and D. And what are the fat soluble vitamins? A, D, okay, perfect, very good. Consists of fractions with varying polarity. Remember, what is the definition of lipids? Maria, out of people. Amelie. remember, it's based on solubility, right? Lipids, remember, different from carbohydrates and protein, they're by class, is by solubility. So they are soluble, majority of them, in hydrophobic solvent. But remember, not all of them. They have some that are more polar. So consists various polarity. Yes. Cannot be completely extracted using ethyl ether. If they have various polarities, if you only want solvent, you think you would extract everything? No, right? So all of the above are correct. Okay, cool. So again, definition of lipids. Lipids are a class of macronutrients that are defined by solubility. So they are majority soluble in hydrophobic solvents, right? Non-polar components. Majority. Like we have some of them that are soluble in polar. We have free fatty acids that are more polar. We have phospholipids that will have the hydrophobic head where the phosphate group and the glycerol are, and the two tails with the fatty acids that be the non-polar fraction. We saw this in also food chemistry. They are divided in three main classes. We have simple lipids. They're just esters of fatty acids. So you have a glycerol backbone esterified to three fatty acids. This is our triacylglycerol. If your glycerol is esterified to only two, you have diacyl, only one, a monoacyl. Remember, you have the hydroxyl groups in the other carbons of the glycerol. We have other fatty acids such as vitamin A esters. Retinyl palmitate is a form. Esters of vitamins, they are usually sold in this form just because they're more stable. Compound lipids such as phospholipids that you have phosphate and other groups, not only glycerol and fatty acids, lipoprotein, glycolipids, riboside, everything that has more than one component, and derived lipids that are the free fatty acids. What comes after hydrolysis? We just saw hydrolysis this morning. Free fatty acids, long chain alcohols, hydrocarbons, fat soluble vitamins. Why do we care about all of this? Because if you want to analyze, you actually need to know what is there, what you need to use to analyze this in food, and how you're going to analyze what type of solvent, and so on. And why is it important to analyze fat content? Why do we measure fat content in food? Perishable shelf life, perishability, right? More fat would mean potentially more susceptible to lipid oxidation, of course, depending on what type of lipids there, but perfect. What else? Nutritional label, right? You see that? Quality, yeah, perfect. Okay, so yeah, nutritional labeling, regulatory requirements like would be an issue. For example, you have a specific standard. When you go to buy milk, right, you have the 2% milk. Like milk, cows produce milk from varying lipid content, usually from 3 to 5. We standardize that to 3.5 as our full fat milk. So usually you take the fat and put it back just to be sure that everything has the same. But then you can standardize that to 2%. You can go to skim milk that will reduce usually to 0.5% or lower. But that's a regulatory requirement or manufacturer specification, a product that needs a specific fat content and stability, shelf life, perishability, because higher fat content means usually that is more prone to lipid oxidation, reduced stability. But again, depending on what type of lipids are there. How do we analyze fat? There are several methods. We're going to go over all of them. We have solvent extraction methods. So we use basically a solvent to extract lipids. We have continuous methods such as goldfish. We're going to talk more about it. Semi-continuous, Soxhlet. Discontinuous, that means batch, Mojo or Mojonier. Elevated pressure and temperature, the supercritical fluid extraction that has been used like recently and for several applications. The accelerated solvent extraction, those abbreviations are in subsequent slides. And also GC method, we can measure fatty acid methyl esters, is a way also of quantify lipids. If you quantify all of them and also account for the backbone, the weight of the glycerol, you can actually have how much fat is in your food. So those are solvent methods. You can have no solvent wet extraction methods such as Babcock and Gerber. They are very well known, especially for dairy industry. Babcock is actually was a professor at University of Wisconsin. And also instrumental methods, infrared, the Foslet method, and the NMR as well are methods used for fat content. They usually need a reference, but nuclear magnetic resonance, and yeah, we're gonna talk about each one of them. When we do solvent extraction methods, the sample preparation and the selection of solvent will depend upon several things. The type of food that we are analyzing, how much fat, how much moisture, is it a low fat, is it a high fat, it doesn't have moisture, it has a lot of moisture, it's milk. What do? We need to think about it. The nature of lipids, are the lipids bound to something? Are the lipids easily extracted? Is a full fat matrix is easy usually to extract? And what extraction methods is available for us? Do we have a continuous? We don't have. We have soft, we don't. Well, what can you do to actually extract all the lipids? So we need to think about all of those parameters to better select the method. And another question. To extract and analyze fat content in a food, the sample preparation may include pre-drying, acid hydrolysis, particle size reduction, and all the options possible. What do you guys think? Yes? All the above. Does it make sense? Let's go over. Why pre-drying? Some food, especially if you're doing Soxhlet, because we're gonna see Soxhlet recirculating solvent. If you have moistures above 10%, you might have an issue because you are diluting your solvent. They usually use hexane or ethyl ether. So we pre-dry, we remove the extra moisture. We do have to hydrolyze our lipid from the matrix. Remember, some matrix, they are attached to sugars, to proteins, how we break down that. So acid hydrolysis goes there. Particle size reduction is always a must. You always need to mill or break down your structure. Why? You increase surface area, you increase the interaction with the solvent, right? So that's all usually what we do before. Some methods do not require pre-drying, but usually all the above is what I would go for. And if you look here, while we do acid hydrolysis, you have percent fat. Don't have a marker. Okay. Dried egg, for example, you see with no acid hydrolysis and acid hydrolysis, you significantly increase for basically all of the compounds the amount of fat because you help release the entrapped fat that you just not can when you just wash with a solvent. Is that clear? Cool. So all the above. So it's a solvent extraction method. So we need to select the solvent. How do we select the best solvent? So the ideal solvent would be a solvent that would not extract any of our proteins or carbohydrates, that would be selected for lipids. Low boiling point. Why? Because it's easy to remove, right? If I can easily remove the solvent, just like heat up a bit or using a rotovap, that would be perfect. Non-flammable, of course, safety purpose, right? We don't want anything that is flammable. Non-toxic, yeah, that's becoming very non-existing. No hygroscopic, do not absorbs water. Inexpensive, right? Is there a solvent with all these characteristics? Would extract, but water would extract protein and carbs, right? So is there a solvent that, nah, no. So this would be the ideal scenario, right? We don't have anything like this. Very common solvents used among ethyl ether, petroleum ether. We also have hexane, for example. We do a lot in our lab like chloroform and methanol. That is just a replacement for ethyl ether and petroleum ether. Ethyl ether is more on the polar side. It's more expensive, great danger of explosion and fire hazard. Hygroscopic, boiling point of 34. They're pretty similar in boiling point. But our petroleum ether, it's more a non-polar side. So you have a polar and a non-polar mixture. Selected for more hydrophobic lipids, is cheaper, less hygroscopic, less flammable. So what do? If we have two solvents, we don't know what to use. A good solution is to mix them with both, right? This is an option because then you are extracting, remember, the more polar lipids that are the smaller free fatty acids, the phospholipids, and also the non-polar ones, the triacylglycerols, for example. So let's start with the methods now. So our first method is the goldfish fat extractor. That is a continuous method. So basically in this method, you have you draw it maybe here, then you guys can, I don't know where to, maybe. You have a beaker, right, and you put your solvent here, right? And then you have a source of heat. And then you have a glass structure that has a thimble inside where your sample is. And then all of this is enclosed in a system. It's closed here. With heat, your solvent is gonna evaporate, gonna recirculate back in your sample, fall down again, keeps recirculating, and your fat gets all here. And what you can do later, you can get this beaker and you can dry, remove the solvent, and then you're gonna have your fat left here. Problem here is that the solvent keeps coming up and down, up and down, up and down. In your thimble, what is gonna happen is that you have a formation of like preferable way, we call channeling, right? Because the solvent is always coming kind of on the same way. So you don't kind of get any soaking of your sample. So it kind of is not super effective in extracting everything because of channeling. So this is an issue. But it's fast. You do a bunch of the same time. And I think with this one, we have burned her eyebrows and bangs. Yeah, ask her. But I think that's she was doing this and she didn't close. And I'm pretty sure that she burned herself when she was a TA for food analysis. But yes, so yeah, this is, yeah, I didn't burn myself, but we're gonna keep with my story too. So this is goldfish, continuous, right? The solvent is always being reflushed. The next one is a semi-continuous. This sucks like, right? What is the difference here? So in Lect, we have usually a round flask. Solvent is here too. We also gonna have heat. I'm not sure if you guys will. Let me put a little down because I'm not sure if you guys will be able to see it. I'm doing. Oh, thank you. Ah, nice. Okay, cool. So then you have here your solvent, your source of heat. Beautiful. Same thing, you're gonna have a glass apparatus on top of here, where you're gonna put your thimble with your sample. Cool. From here, you have something like this. And you also have something. Let's go. And on top of this, you have a condenser. Right? So what happens here? You put your solvent here, hexane, anti-ether, whatever you're using. Again, heat, solvent, evaporates, go up, 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 go here, heat the condenser. What happens? Becomes liquid again, precipitate's gonna go here, but it's not gonna go out. It's gonna actually start all like getting around your sample. It's gonna soak your sample. Once it gets high enough, it drops down here and get back here. So in this oxide, you have the soaking step. And this is very, very useful because now you are increasing the time that your solvent is in contact with your sample, helping with extractability, but it's not a continuous method, right? But this is very useful and you can do in series like it's showing here. So basically you have the same draw. Turn off the light so you guys can see. a draw right there that is showing the same thing where the thimble is, where you weigh your sample, where the solvent gets in contact with your sample for a while, and then you don't have those preference channeling, like the channeling being formed. So that's another advantage of Soxley. How do we actually determine how the fat content from those methods? Both for goldfish and Soxley, they are gravimetric methods, which means at some point we're gonna have to weigh our sample. We can calculate the percent of fat on dry bases. 100 times multiplied by the beaker or flask plus fat, like right there, and minus the weight of the beaker. So we know how much fat's there divided by the amount of sample that you had in the beginning, right? It's just fat over sample. That's pretty easy. Or the other way, you can indirectly measure by how much sample is left. So if here in your table, you know how much, you should know how much sample you add 10 grams, right, of sample. And then you extract all the lipids. You can weigh again. And you know the weight of the thimble, you know how much sample was there. Let's say now it's 8 grams of sample. You know that 2 grams were extracted, they were fat. So indirectly, you know how much fat's there. And then you know how much sample you had. You can calculate again the amount of fat. So 2 methods, or by weighing the fat or by weighing how much you lost in your sample. Is this clear? Question for you guys. If the percent fat on a dry basis of my product is 15%, if I want to see in wet basis, knowing that the moisture is 20%, how much would that be? You guys can do it. You have a minute to do it. We did this exercise too, similarly with proteins. I don't know if you guys remember that from your class, but we can do it together too. Turn on again. First question, is it gonna be higher or lower? I like the okay. Cool. Does anyone have a number? Yes.
Well, what if it's 100 minus 20%, 100% minus 20%, and then it's gonna be 15 over 80%?
Okay, we're gonna. So, does anyone got a number or no? No. Okay, let's do this together then. We know that in dry bases, right, our lipid content. So lipid content, dry bases is how much? 15, right? How much solids do I have in dry bases? If it's dry bases?
80%?
It's dry bases. 100%, right? Yeah. So no water whatsoever, right? 100% solids. Now I want to know in 20% moisture. How much solids do I have now? 80%. 80% solid. So what I want to know is my lipid content now. So we have here 15 multiplied by 80 divided by 100. How much is this? 12. So lower, right? It's everything that is in this line. But everything that is, when you increase like this dry bases, will always be the highest value. When you have like more, you have more things to to divide your total, right? So yeah, that's why it's lower. Is this clear? So if just like if it was like 50%, would be half of the value, right? Would be 7.5. Okay. Yep, a 12%. Mojo or Monjonier is another discontinuous method. If you work in my Pam's lab, you probably already, or any lab in this, or George, do you do this too, Emma? Mojo or no?
I haven't.
You haven't? Okay, but probably they don't like to do this. Okay. It's also a gravimetric method. is treat samples in series with, depending on the method, but usually use ammonium hydroxide to solubilize all the protein. Ethanol is to avoid clump formation because you can have clump if you have too much protein. Ethyl ether and petroleum ether, remember, two different polarities. We are extracting everything. And we don't need moisture removal because we are hydrolyzing. We are adding all this ethanol, ammonium hydroxide. And for samples that are rich in carbohydrates, remember, lipids can bond to carbohydrates and very hard to separate. Such flours, we do add HCl. We end up adding HCl to almost all the samples just to be sure that we are hydrolyzing everything and breaking down. But officially, you only add for rich, you only need it for protein, carbohydrate-rich samples. And this is this weird glassware that is very expensive, by the way. I think $700 each one of those. So that's why people do it very carefully. And you have to shake. You use a lot of solvent, not as much as Sockless. Sockless like a 300 ml-ish of solvent. Here's 25 of each, 2 times. Extract. And then again, you pour, you dry the solvent, you know how much fat you have. Not as common because it's a little expensive, but it's been used more and more. Supercritical fluid extraction. So here you work on the supercritical state. So you have carbon dioxide is what is the state in regular pressure, like temperature and pressure? It's a gas, right? If I put a lot of pressure, a lot of temperature, I can move this to a supercritical state. You see the end of our equilibrium phase, a diagram, and then you have your supercritical state. It's not a liquid, it's not a gas, it's something between that has very interesting properties, such as a non-polarity. So it can act as a non-polar solvent, but it's a green solvent, which is pretty cool. So you're not using anything flammable here. The other great advantage is when it comes out of the equipment, CO2 becomes again vapor, or vapor, no, like becomes gas and is removed from the system. So they don't need a desolvatization step. It's being used for high quality like oil or those essential oils. The definition of essential oil is actually something extracted by hydrodistillation, but a lot of people call essential oils everything. But yeah, that's how we extract, for example, from clove or from lavender, a green way to extract those non-polar components. Again, here you can tailor conditions to shift a bit polarity, but you only have one solvent. If you want to like extract everything, you can do co-extraction with methanol, pretty used to in the industry. And then you can also use this as a sample prep for GC, very expensive sample prep. But in my lab, we do chloroformethanol and extraction. Like Vichy knows a lot about this because we do this a lot. And the fat is precipitate in a way. It's like just because the solvent goes away directly. So not, and you can weigh how much fat you have. Pretty straightforward system. In Davis, the lab that one of the labs that I was working, so I did my postdoctoral research at UC Davis, and one of the labs we just got one supercritical for a benchtop one, and it's a very expensive machine, it's $120,000, right? But the PI bought the machine without buying any installation service because that's the budget that we have. And then she was like, "You can install it," and I was like, "Cool, yeah." So I got the manual, I was installing it, like lots of parts to attach and everything. Oh, it was not that hard. And then I called the person that was helping, and then you're like, now you need to test it. Those things, they get 300, 400 bar pressure, right? And he's like, oh, if it makes a weird noise, run. And I was like, that's not a great advice. And then I was turning on it, it's like, and I was like, is this weird? Is this, should I die? Well, we are all gonna die now. I don't know. But it worked. It's working fine. And it was pretty cool. We extract almond oil with it. I analyze all the oil. Those beautiful. They smell is phenomenal. But it's very scary. Like it makes a lot of weird noise. Yeah. And then the other thing that I was telling my students yesterday is that Davis has like the new beautiful Mondavi Center that received a lot of money from the winery because they don't want to pay tax. But anyway, it's a beautiful, yeah, they donate, I think 100 million, right, for that building. Yeah. Anyway, beautiful, beautiful food science, brand new. But I had to do the SOXLET analysis in another lab that was, what, 2 miles from there? And so I would get my bike, put my hexane there, and just ride my bike with a couple of gallons of hexane. Not safe at all. And I was the lab safety coordinator. But yeah, not do it, don't do it. But it was the easiest way to get there, and it was just temporary. But yeah, but I didn't burn myself. Anyway, getting back here. But that was fun. Okay. Another way that we can do extracts is called elevated pressure temperature. It's similar to the supercritical, but doesn't reach that level of supercritical. So it's a little less dangerous, let's put like this. It's just put some pressure so you keep your solvent, you can heat up without making it becoming a gas, so it extracts more. It's used also for extract fats. You can dry and wait. Same thing. You can do static or dynamic. It has a bunch of valves that you can open and close. And the dynamic system is usually more efficient, but you use way more solvent. So it depends on what your goals are. Just saw this in demos in a conference. Never saw this actually working, but it seems pretty interesting. Okay, done with all the solvent ones. Now we have the no solvent ones. No solvent wet extraction methods. So as I mentioned, they were named after Babcock. There was a professor in Wisconsin. So guess what? This is for dairy, right? Different from the solvent methods that you actually have to have a solvent extract, then you get the solvent, dry the solvent, weigh the fat, or weigh different by difference your sample. This one you weigh, you have an amount of volume of your sample. In those flasks that have like, see, they have measurements for volume. And then you add sulfuric acid to digest proteins. Generating heat is an exothermic reaction. So your fat become like liquid. And what happens with the fat? If you have fat and water, fat goes top, right? It's less dense. So you're gonna have fat on that area right there. So then you can measure how much you have. So those different flasks are for milk, cream, and the cheese. That's why it has this opening here, because you have to put your sample there. You can just not just pour. So you do this digestion with sulfuric acid. You centrifuge. There is a specific centrifuge that fits those tubes. And after centrifugation, you can measure fat volumetrically. So you have a volume by volume. But if you know the density of the fat and the milk, the defatted milk, you can actually back calculate and know how much fat is there in grams. Advantage here, no need to dry. It's pretty specific for dairy, but it works kind of well. It only needs the one reagent, sulfuric acid. There is no all this need to do solvent. And an extract amount of milk, cream, and cheese is added to, and they will have a specific amount of sulfuric acid. So it's a straightforward method too. The other method, this is a French researcher, Gerber. Very similar. The difference is the shape of the glassware. And also that uses not only sulfuric acid, but amyl alcohol. Also helps disperse, avoids clumps. And as I said, the bottles will differ in shape. Is a simple and faster method. Again, water application in dairy, and prevents the charring of sugar, like becoming black, Once you add this, it helps this distribution of heat better, so you don't have the formation of the black compound that you're gonna see more in Babcock. So that's one issue. When you are doing Babcock, when after the centrifugation you see a black char, this method will help with that. And I believe we do have one exercise, and I'll give you guys some time to do it as well, because this class is short, so you guys probably gonna be done a little earlier, which is great. But both Babcock and Gerber methods, as I mentioned, they are volumetric methods. If milk fat density is 0.9 and milk density is 1.032. So again, lipids less dense than the fat, than the milk. If the percent of fat on a volume basis is 3.55, what would be the percent on wet weight basis? So what I want you guys to think here is we are measuring volume, right? So 3.55 means 3.55 mLs in 100 ml. So with this information, I want you guys to try to solve this. Since we have time, we'll give you like 5 minutes to give this result. So we know volume. We have 3.5 mLs of fat in 100 mLs of milk. That's what we have. Do you have a lab on this, Richie? Yeah. Oh, you do have software. What software do you use in software? Just a curiosity. And what samples do you do it, you know?
Almonds, cheese, and baby cereal.
Oh, very cool.
Yeah.
A very rich in carbohydrate. Oh, nice.
What?
A very like baby cereal, very rich in carbohydrates. Yeah.
Yeah.
Almond and all.
That's next person.
Oh, nice. So nobody did this yet.
No.
I'd like to make here just did you guys figure that out? Good. We do have time. But do you have the answer? I'm just kidding. Ah, thank you. Okay, give you 2 more minutes and then we can solve it together. Hmm?
Like make them students expect.
Yeah. Cool. And you're gonna do more job of the same sample? Cool. Okay. Does anyone have an answer? I'm already. Time percentage. Still working on it. Okay. Can give you 1 more minute. Well, yes. Pretty. Yes, that's right. Yeah. Good. Okay, we're gonna do the. Did you guys have a got there? No. Okay. Let's see why. Maybe. Okay. What are the densities? Let's go here. Again, so density of what is, I don't remember. What density of the fat is 0.9 that is there?
Yeah.
0.9 what? What is the unit? Grams per ml. So this is the fat, right? What is the density of our milk?
1.032 grams.
1.03. Perfect. Okay, what is density? Perfect. Mass divided by volume. So I know that my percent fat, right, is 3.5 mLs in 100 mLs. Okay, but I want to in grams, right? I want the mass. What is mass? So if I isolate mass, mass is what? Volume multiplied by density, right? Okay. So if I want my fat percent in relation to mass, this would be the mass of fat divided by the mass of my milk. Let's replace mass of fat by this one, right? Because I know my volume, I know my density. So volume of fat multiplied by density of fat divided by volume of milk multiplied by density of milk. So here I have volume of fat is 3.5. Density of fat is 0.9 grams per ml. Volume of milk?
100.
Perfect. 100 multiplied by a density 1.032. Right? So this is a percentage, right? So no unit. 3.5 multiplied by 0.9. Thank you. 3.195. And here is just 100. So this is 103.2. Can someone divide this? 3.10. 0.09, and then I want a percentage, right? So I multiply by 100, and then I get 3.09%. Right? Is this clear? Yes.
So where does wet basis and dry basis come from?
Okay, yeah. So we are talking about volume and mass, fat percentage, right? So this is a fat percentage on whatever moisture content this is. So this is in wet basis, right? But I don't know what is the moisture content of my milk because nobody told me. Usually it's 92%, but yes. Because this is just because this method measure volume. So this is not related to dry and wet basis. This is just how we could convert something that is volume in mass because they are pretty close to one, the density, but it's not one. So if I just say, oh, it's 3.5% fat in volume basis, it's not what we usually do. It's usually we count it in mass. And if you see, it's a little lower, right? So if you want to, for example, standardized milk, that is usually standardized at 3.5% fat in mass base, not in volume base. So you need to back calculate. Even though this method is super fast, you still need to do a little bit of back calculation to get. But this 3.9 is for the milk. Milk usually has 90% moisture, so 10% solids. So what would be in dry basis? Since you want to know, that's say it again. So yeah, so like moisture content in milk is usually 90%. So this, let's say that this is for something that has 90% moisture. In dry basis, how much this would be? So this has about 9% moisture. Now, if I want to know in dry basis,
Would you just do 3.195 divided by
or 3.
the mass of the fat divided by the mass of the solids?
Sort of.
Is it 30.9%?
30.
Yeah, or 309%?
Oh, 330. Yeah. So let's do that. Yeah, that's so how do we do this, right? So it's 3.09. And how much moisture? And how much solid? 10, right? If I go for 100% solid, this will be 10 times more, right? Don't even need the like, it's just 10 times more. So you were right. That's beautiful. 30.9%. So see, like in dry base, milk has like about 30% solids.
So it's the same.
30% fat.
Like a ratio.
Say it again.
So it's the same, like it's a ratio basically.
Yeah, because and now you like milk is mainly liquid, right? So 90% moisture. So of course it's 30% fat when you dry. This is what you get in milk powder usually.
Oh.
Makes sense? Okay, but this, just so you know, like this is not related to this part. This is just how to calculate based on this method that is actually a volumetric method, not a gravimetric method. Is this clear for everyone? Oh. Okay, we have 4 minutes. Yep. So here just showing 3.55 multiplied by 0.9, 3.195 is the same ratio, like rationale. I just like to put like this, just because it's everyone thinks differently, but for me, it's like what makes sense. But you are welcome, I believe, to do anyway, any form, as long as you show what you did in the exam. That's what I believe. And the last part, okay, 5 minutes. Instrumental methods, infrared spectroscopy is based on absorption on the infrared. Energy by the fat, you usually need a calibration. So you usually, like people that do this is very high throughput data, but you need a calibration from usually gas chromatography, mass spectrometer, gas chromatography, flame ionization to actually feed your infrared. The Fo's loss method is a function of the specific gravity of a sample and a solvent. And then you can convert directly to fat percent using, you have this chart for that, and you have to use a specific solvent. And also the nuclear magnetic resonance. The principle is very complex of this machine, but the method itself is simple and rapid and can allow you also a degree of automatization and computerization. I'm not seeing this as much for fat content because it's kind of expensive as well. You can, this is proximal and on lab. I don't know if this will be.
It's like talking about what they're gonna do.
Okay, which I'm not sure if you want to talk about, but anyway, and that would be, thank you guys for today and happy Halloween. Yes, and I hope you enjoy. Yes. And this is baby in a ducky costume. Yes.